Today, I'm going to talk about three different theorems. We're going to, first of all, talk about Rolle's theorem, which we're then going to use to prove Cauchy's mean value theorem, which we're then going to kind of alter and turn it into Lagrange's mean value theorem. And, the prize at the end is, of course, Lagrange's mean value theorem. It is a classic theorem stating that, that's what I say for every theorem. It's a classic theorem stating that, if you have, an interval A and B, and you have a function, for example, like an exponential, bang, and then if you draw the tangent line of that function from A to B, so, just the slope of this, a point A to B, well, then we're saying that this average slope, this average, rate of change of the function, at one point in this interval has to equal the instantaneous rate of change. So it at one point has to equal the actual slope of the function. So imagine I just shifted this graph down here, and again, boom, this is exactly tangent to this random point over here, let's say like C0. So at one point, the instantaneous rate of change has to equal the average rate of change. Is that intuitive? Is it not intuitive? I don't know. I feel like it could be, but it's still slightly surprising maybe. Well, anyways, we're gonna prove it. So first of all, we have to talk about Rolle's theorem to complete the other two proofs. And basically, Rolle's theorem is just a theorem stating that if we have a function that's continuous in the closed interval, including AB, and if it's differentiable just in the interval AB, not including AB, well then, if f of a equals f of b, there exists a point. It's the easiest to draw this. I have a over here, I have b over here. The function just equals the same thing at a and b. Well, then we know that there exists such a point x0 inside the interval that the derivative at x0 will equal 0. So there exists a point where the slope will be 0. And again, we can either have this case, as we're going to see, or we can have this case where the function is just constant the whole way through. And, of course, then it's constant everywhere. So it makes sense. It very much makes sense. The proof is also very easy, and it makes sense. But first of all, I just want to talk a little bit about why we want it to be continuous in the closed interval, but differentiable in the open interval. Well, actually, you're going to see the proof right now. First of all, if, in a first case, if the maximum value, f max, of the function equals a, equals b equals f min. So again, if the line is just a constant line, well then the function is constant, and f of x equals 0 for every x in AB. And we don't even need to look at the derivative. We just want it to be continuous, but basically, in this case, if our function, if we have our interval here, if it's just a constant function, well then of course its derivative is going to be 0 everywhere. But then in the second case, we're going to actually need the derivative, but we're only going to need it in the internal points, because by the extreme value theorem, or the Weierstrass theorem, if we have a continuous function, so Weierstrass, I think I spelled that wrong, theorem. So if we have a function that's continuous, so if you have a function that's continuous and it's defined on a closed and bounded interval, well then we can say that it must obtain a maximum and a minimum value in that interval. So must have f max and f min. And that makes sense. I'm writing it very quickly because it's not really important. Of course it makes sense. If a function is on a drawing our function here, like if we have a closed bounded interval, then obviously the function has to have a minimum and a maximum somewhere. It could be at the edges of the interval. It doesn't have to be in the edges of the interval, but that makes sense. Well, since, oh wait, I'm running out of space. I thought it was gonna take less space, but since it has to obtain a maximum and a minimum by the Weierstrass theorem, then by Fermat's theorem, which is another theorem, you don't have to worry about them too much. But Fermat's theorem just says that if a point is a maximum or a minimum, and the function is differentiable at that point, well then the derivative at that point, I'll just call it x0, has to equal 0. So that's Fermat's theorem. We basically use Weierstrass theorem, Fermat's theorem. It's very simple stuff. It sounds very formal, but the Fermat's theorem is just saying that if we have a function defined in a closed interval AB, and if a point is a maximum or a minimum, and if the function is differentiable there, well then at that point the derivative of this function has to equal 0, which of course makes very much sense. So basically, if our maximum and minimum happens on the edges, well then we know the derivative is 0 everywhere. So we just want it to be continuous. But in case the maximum and minimum are not on the edges, well then we need to say that the function is differentiable at that point, so that then we can use Fermat's theorem and say that the derivative there is 0. Very, very classic theorem. It makes a lot of sense. And now we can move on to Cauchy's mean value theorem. And now here we're going to see that it has the same assumptions as the as Rolle's theorem, because again, we're just going to be using Rolle's theorem to prove this theorem. It has a very clean proof, as you're going to see. We're going to be looking at two functions, f and g, from the same interval to r. And our third assumption is going to be if the derivative of g does not equal 0 for every x in AB, well, then we can say that there exists a point, I think it's called psi. It's such a, I don't know why people choose like this letter for the proofs. It's so hard to draw, but it's, yeah, there exists a point psi. You can just, say there exists a point c or something in the interval AB. So internal point, it's internal point of the interval. It's not on the edges, such that f of v minus f of a over g of v minus g of a equals the derivative of f at that point over the derivative of g at that point. The intuition, like the geometric intuition behind this, is like really hard. These are two like parametric curves. We're talking about an interval AB, and then we're talking about two curves. This can be f, maybe like this can be g, and then we look at the slope. I mean, then we look at f of b minus f of a and g of b minus g of a, and then we say that this quotient equals the derivative of these two functions at one point. The intuition for it is kind of weird. It's not even that important. We'll see that Lagrange's mean value theorem has a way nicer, has a way nicer image, and it's just gonna be like kind of a simplification of this theorem. But basically, how do we prove it? Well, the proof is actually really clean. If we start with the proof right now, since g of x does not equal 0 for every x in AB, as we said over here, well then we know that by Rolle's theorem, g of a does not equal g of b. And this is kind of a slight, like, it's because Rolle's theorem doesn't, basically, like, what Rolle's theorem is saying, that if g of a equals g of b, then there has to exist a point c such that f of c equals 0. If there exists a point such that f of c equals 0, that doesn't mean that this is true. But if this is true, then this has to be true. I can give a quick example right now. There can exist, we can have a function like this, that goes like this. And again, f of b, or g of a does not equal g of b. But, there still exists points where the derivative is 0. So, this doesn't guarantee this. But as soon as we have that g of a equals g of b, if you have a constant, if you have a function where g of a does equal g of b, well, then the derivative has to be 0. And since the derivative is never 0, then g of a cannot equal g of b, because if g of a would equal g of b, then there would be a point where the derivative is 0. So this is kind of how we use Rolle's theorem to use Rolle's theorem to show that this can be true. And now, since this can be true, that means the denominator is not equal to 0. And because the denominator is not equal to 0, then, we can cross multiply this, because otherwise it would be undefined and we can't cross multiply. So now, if we cross multiply this function, we get f of b minus f of a times, actually, I want to write I want to write this on this side. So this times f of b minus f of a equals then this times this, and I'm just going to subtract it to the other side. So minus f of psi g of b minus g of a equals 0. So, I just cross multiply this and put it on the other side, and put everything on one side, and we get this expression over here, and this equals 0. So basically, if we come to this expression, then, if we just divide, if we put this on the other side and divide, we get to this original expression. So now, how are we going to get to this expression? Well, we're going to define a new function. It's kind of an interesting trick, but it's a pretty cool trick. We're going to define a new function called h of x, and our function h of x is just going to be g of x times f of b minus f of a minus f of x times g of b minus g of a. And our newly defined function looks very similar to this function over here. And, as we can notice, these are constants. F of b minus f of a, this is just a number. B and a are like, predetermined numbers. And again, this is also just a constant. So it's just a function times a constant minus another function times a constant. And that's how we define our function h of x. And now, since h of x is, a difference of two continuous and differentiable functions, h of x also has to be continuous and differentiable, obviously. And now the crazy part is, let's just check out what h of a equals. Well, h of a is going to be g of a times f of b minus g of a times f of a. I'm just, multiplying this out, and then minus f of a, x turns into a, times g of b, plus, because minus and a minus makes a plus, of f of a g of a. And now what happens over here, we're going to see that we have that something's cancel. We have g of a f of a minus g of a of f of a here, and we have plus g of a f of a here. So this cancels, and what we're left with is just g of a f of b minus f of a g of b. So that's what h of a equals. And oh my goodness, I really underestimated how much space this is gonna take. Let me just shift this over down here. But we are almost done. You know, the proofs are very easy. Now let's this is what h of a equals, and now let's just check out what h of b equals. You know, just out of curiosity, what does h of b equal? Well, that's gonna equal g of b f of b minus g of b f of a. You're gonna see something crazy is gonna happen, and then we have minus f of b g of b plus f of b g of a, and again we have some cancelification. We have g of b f of b here, and we have minus g of b minus f of b here. So this just simplifies to, I'm gonna put the positive side first. This just equals to f of b g of a minus g of b f of a. And now the craziest thing ever. Well, look at this. F of b g of a, f of b g of a minus f of a g of b minus f of a g of b. These are the same things. The functions, they equal each other. We have that h of a equals h of b. And now the craziest thing, well, do you remember Rolle's theorem that we just proved? So we have two continuous and differentiable functions, and we have that h of a equals h of b. So again, we have a function that's continuous and differentiable on the interval, and we know that on the interval a b, we don't know how the function looks, but we know that eventually, at the point a and b, the function is equal. That means we can use Rolle's theorem that we just proved. And what does Rolle's theorem say? Well, if scroll back up, Rolle's theorem says that there exists an interior point psi in our interval AB such that the derivative of our function at this point will equal 0. That's exactly what we're saying. And again, this is our function. This is our function h of x. We know that there will exist a point where its derivative is 0. We don't know where the point will be, but there will exist a point because h of a equals h of b. So what is the derivative of our function h of x? This is our function h of x. Well, these two things are just constants. This is just a constant. I can name it c1. This is just a constant c2. So the derivative of h of x will just be, the derivative of g of x times this constant c1 minus the derivative of f of x times this constant c2. That is just the derivative of h of x. So we know that there exists a point epsilon where this will equal to 0. So what is that point? Well, we can say right now that the derivative at this point epsilon will just equal the derivative of g at this point epsilon times f of b minus f of a, which is just our constant, minus the derivative of f at this point epsilon times g of b minus g of a. And that equals 0. This equals 0. This is exactly what we wanted to prove. Again, now we can put this on the other side, we can divide, and we get exactly this expression over here. So in a really clean way, by defining a new function, we just showed exactly what we wanted to show, and all we needed to do was use Rolle's theorem and a smart smart way to define a new function. And of course, we also have to assume that our functions are continuous and differentiable on the interval. That is very, very clean. And now we basically, by proving Cauchy's mean value theorem, we basically proved Lagrange's mean value theorem too. Because again, look, we had the same assumptions. We wanted to be continuous and differentiable on our intervals, on this closed interval, on this open interval, on this closed interval. Again, because we need Rolle's theorem, and we're gonna see that Lagrange's mean value theorem, which is our clean thing, that the derivative, the average slope, will have to equal the actual slope at some point. Well, that is just a special it's just Cauchy's theorem chosen when we choose g of x equals x. Because look, if I'm just gonna copy down Cauchy's mean value theorem, which is over here, and now let's imagine that we just, one second, bang. Now just imagine that we choose g of x equals x. So what's that gonna mean then? Well, then we're gonna have f of b minus f of a over, well, what if g of x equals x? That means g of b just equals b. It just gives you the same value, and that means g of a just equals a. So we're gonna have f of b minus f of a over b minus a, and that's gonna equal f, the derivative of f at this point psi, over, well, what's the derivative of a constant function? The derivative of a constant function is just 1, so over 1. So exactly what we're trying to show over here is just not a generalization but a degeneralization of Cauchy's mean value theorem. That is Lagrange's mean value theorem. So by proving Rolle's theorem and by proving Cauchy's mean value theorem, we get for free Lagrange's mean value theorem. And that's the clean, that's the whole clean theorem. That's the one with a clear intuition, the one that's most useful, maybe, I don't know. But again, let's just see. I'm going to draw it a bit nicer. We have a function a and a function b, I mean an interval a and b, and we have our function, let's say it's going to be something like this, and then we draw a tangent to this function, I mean the average tangent, the average rate of change from a to b. And if we shift over the tangent, I think we shift it up in this case, at one point, we just shift it up at one point, the slope of our function will exactly equal the average slope. It makes sense, but again, it is, it's not super intuitive to prove. The proof isn't that easy. I mean, again, it's a very simple proof, but you can't just, do it in 1 second in your head. But that is basically Lagrange's mean value theorem, and we got it from Cauchy's mean value theorem, which is a bit more complicated to understand what it actually means geometrically. I still don't even fully get it. And then we also use Rolle's theorem. Rolle's theorem is a very classic theorem which is applied in many places. And we indirectly also use Weierstrass's theorem and Fermat's theorem, but these are again also very simple theorems. So yeah, that is it. There's everything I wanted to say. Thank you for watching, and yeah, see you next time.